Hello everyone, this is Patel Alohar, Assistant Professor, Department of Electronics and Communication Engineering at Engineering College, Lahore. The e-lectures is prepared for RT syllabus antenna and propagation for 6th semester SC student. In last lecture, we have discussed Hungen principles and rectangular apertures antenna structure. In these lectures, we will discuss circular type of the apertures and design consideration of rectangular and circular apertures antenna. Okay, so circular aperture, basically it is a widely used microwave antenna is the circular aperture. One of the attractive feature of this configuration is simplicity in construction. In addition, closed form expression for the field of all the modes that can easy over the aperture can be obtained. The procedure followed to determine the field radiated by the circular aperture is identical to that of the rectangular as a summarized in section 12.3. The primary differences lie in the formulation of the equivalent circuit, equivalent current density Jx, Jy, Jz, Mx, My and Mz. Okay, so this is the basically circular aperture design on infinite ground plate. This is the infinite ground plate. This is the circular, and the coordinate system we have in this design cylindricals. Okay, rho, phi and z. This is the coordinate of the cylindrical system. Okay, the difference path from the source to the observation point r dash cos sine and the differential area ds. Before an example is considered, these differences will be reformulated for the circular aperture. Because of the circular profile of the aperture, it is often convenient and desirable to adopt cylindrical coordinate for the solution of the field. In most cases, therefore, the electric and magnetic field component over the circular opening will be known in cylindrical form. That is the E, rho, E, phi and Ez. Similarly for H, field, phi, theta and z. Okay. The most convenient position for placing the aperture is the form in the figure 12.16, and plane is xy. The transformation between the rectangular and cylindrical component of Js is given in this. Basically through the rectangular to the cylindrical transformation, we can basically this is the x, y, and z component coordinate system. And this is a phi. This is cylindrical, rho, phi, and z. So we can convert the from rectangular coordinate to cylindrical coordinate using this matrix. Okay. Now we discuss. This is the table completely. First we discuss aperture, uniform distribution aperture on ground plane. This is the aperture design on the ground plane. The electric field is constant. The electric field is uniform from the structure. Okay. In that case, the electric field in direction of y is constant less than equal to radius of the aperture. Okay. Or then this condition for the TE11 mode distribution aperture on ground plane. Basically in circular, the TE11 mode is exists, not TE10. But in case of the rectangular, there TE TE10 mode is exist. So circular represent always TE11 modes. So in case of TE mode, the electric field is not constant; it vary in the form of the in direction of rho and theta in the term of the sinusoidal variations. Okay. So this is the field, far field zone. We take Z equal to K sin theta and Ci and C2 C. This is the coefficient. Putting this coefficient, and then we can calculate the field component, electric field and magnetic field component. Okay. This is field component for the uniform distribution aperture on ground, or this component for the TE11 mode distribution aperture on the ground plane. Okay. And this pattern represents half power beamwidth of the uniform aperture. Okay. This is half power beamwidth for uniform, and this is the TE mode. First null beamwidth for the uniform, this TE11 mode. First lobe for E plane and H plane, this given is that. Okay, for a uniform, and this is for the TE11 mode. And directivity of the aperture, this is for the uniform distribution aperture, and this is the TE11 mode aperture. Okay. Now we can discuss the design consideration. As is the case of the for array, aperture antenna can be designed to control their radiation characteristic. Typically, the level of the minor lobes can be controlled by tapering the distribution across the aperture. The smoother the taper from the center of the aperture toward the edge, lower the side lobe level, and the larger the half hour beam width, and conversely. Again, so according to the tapering, we can control the aperture gain and directivity and beam width. Therefore, a very smoother taper, such as that represented by a binomial distribution or the others, would result in very low side lobes but larger half power beam width. Design rectangular aperture. For a rectangular aperture of dimension A and B and with uniform distribution, the procedure to determine the optimum aperture dimension A, B to maximize the directivity at the edge of angle theta C of the given angular sector 0 to theta C. Basically, in design consideration, we design the rectangular aperture and calculate the A and B value. A is width and A is length and B is width of the aperture, rectangular aperture. So, to determine the optimum dimension B of the aperture so that the directivity is maximum at the edge of coverage angle theta CE. Theta C means edge of coverage of the E plane of an angular sector 0 to theta CE in the E plane is given by. So for in case of E plane, we calculate B equal to lambda by 2 sine theta CE. Or similarly for the H plane, we calculate A equal to lambda by 2 theta CH. CH means coverage angle for H plane. Okay. Since the aperture antenna is uniformly illustrate the directivity of the based on the optimum dimensions of A and B. According to A and B dimension, then we can find the directivity 4 pi lambda square to AEM. Okay, where AEM is A and B values for E and H plane. So putting this A or B value, then we will find the directivity of the rectangular aperture. Similarly, we discuss for the design of the circular aperture. In that case, we have to find only the value of A, radius of the aperture. So a procedure similar to that for the rectangular aperture can be used for the circular aperture. In that case, it can be used for the circular aperture with uniform distribution as well as a taper, parabolic or parabolic with the pedestal. For a circular aperture with uniform distribution, the normalized power pattern multiplied by maximum directivity can be written as this. Okay. Normalized power pattern, basically this is the normalized power pattern in terms of the radius of the aperture and theta. The maximum value curve when theta equal to 0. However, for any angle theta equal to, the maximum of the pattern occur when Ka sin Qc equal to 1.84. At this condition, the maximum pattern can be appear. So, using this equation, we can calculate the A value. A equal to 1.841 lambda divided by 2 pi sin Qc. Okay. Now simplify this equation. This is the lambda by 3.413 sin Qc. Okay. Therefore, to maximum directivity at the angle of A, theta equal to Qc of a given angular sector 0 to theta c, the optimum radius of the uniform illuminated circular aperture must be chosen according to the 12.61a, the maximum value of the which occur theta equal to 0. Okay, this is the 2 pi a square, while age of the angular is equal to the this value. Theta equal to 0, the value is this, and at theta equal to Qc, the value is given in that form. Therefore, the value of the directivity at the edge of the desired coverage theta equal to theta c related to the maximum value theta equal to 0. So this is the value of minus 3985 dB. Since the aperture is uniformly illuminated, the directivity based on the optimum radius is 4 pi lambda square AP. What is AP? Area of the circular. So we put in this value from the getting from this value we have putting in this equation. Then this is the simplified equation of the directivity of circular aperture. So this is the 1.097 pi divided by sin square theta c. Okay. This is the using the value of A, we can calculate the design circular apertures. Okay.